Welcome to Google Cloud AI Developer Relations Training for Virtual Data Scientists. This session we will be focused on autoencoders. My name is Andrew Furlich, and I'm a staff member at Google Cloud AI Developer Relations. So we're going to cover first what unsupervised training using autoencoding. That means we're going to train without any human labeling, but that does not mean there are no labels. We're then going to discuss a deep neural network autoencoder and then a convolutional neural network autoencoder. And for both of them, we're going to show how to use them to learn to compress and decompress a data set. Then we're going to cover a denoising autoencoder, learning to denoise an image. And then finally, we're going to show how to use autoencoders for pretext tasks and pre-training of a model to learn essential features. So let's start with the basic principle of an autoencoder. So here at the input, we're going to have some high dimensionality input. And for our purpose, just assume that's an image. And the encoder part is going to, sequential or progressively reduce the amount of information. And many have seen that chart where it kind of comes down to this. And when you get to a very reduced amount of information, it's low dimensionality, we call it the encoding, or in other words, the latent space. Then on the other side of the model, it's all inverted. We're going to learn to unpool the information here. We call it a decoder. It's usually a mirror or a symmetric image of this side, just flip the other direction. And it's going to output some high representational output. Now, a couple common things are used for. One is the identity function. The identity function is simply f of x equals x, or you can say, if I gave the model some image x, it would output the identical image. Other forms or functions, we call them translational function. Given some deterministic function for x, given x, our input, we simply use g of what we know g of x to be the label. So these are examples where there's no human label, but we can use the characteristics of the function to auto-generate the label. So let's look a little bit more at the architecture of autoencoders. So on the encoding side here, you're going to have a sequence of layers where we're going to do what's called learn pool. That is, these layers are going to learn the best way to pool the data. Okay. And we're going to progressively pool it. That means the data is going to get smaller and smaller and smaller. Okay. And then this is what we call the encoding learning. And the output of that is what we call the latent space. Okay. And then we're going to take that latent space and we're going to just do the reverse. We're going to learn, we're going to have a sequence of unpooling layers. We're going to learn the best way to unpool that's going to restore back to the same dimensionality. Okay. And that's typically symmetric to the encoder. So we can also look at it this way. The encoder performs what we call representational learning on the input here to learn the function f of x that generates this latent space we call x prime. Okay. And this latent space is how would I say it, of a much lower dimensionality. And then the decoder takes this latent space, x prime, and does what's called transformational learning from the latent space to some type of reconstruction of the image into a high dimensional space. So let's start with the identity function. This is usually where everybody starts with an autoencoder. And as I mentioned, it simply means given some function of x, it outputs x. Since the latent space x prime is of low dimensionality, we typically refer to this form of autoencoder as learning the optimal way to compress images in a data set. That's the encoder. And then decompress the images after they've been compressed. That is, this data set, your data set represents a distribution. And when it's learning, the autocoder is learning is the best way to compress the, say, images for your distribution and then decompress them. What's important to remember is it's specific to the distribution. So if you apply it to a different distribution, you can't expect to have the same level of quality, if any, of the compression and decompression. Okay, so let's code a DNN version of an encoder. Okay, so what it's going to take is a parameter. Well, first it's going to take the input, right? And then this parameter layers. And consider this like a list. And it's going to contain a sequence of how many nodes at each layer. And we're going to presume, because we always progressively pool, that that number is going to get smaller. So the first one might be 256, then 128, then 64. We're assuming we're doing this for an image, so we're going to go ahead and flatten it into a 1D vector. And then we're just going to spin around here and go through this list layer. And for whatever nodes we have at that layer, we just create a dense layer. Then the output of that, the final output of all that progressive pooling, is our latent space. So writing an encoder for a DNN is really straightforward. The decoder, we just want to, in a sense, say we really want to take this layers, the same layers list that we used for the encoder, but go in the reverse direction. So you can see I'm doing that here in the for loop. I'm just going in the reverse direction, and I'm recreating all these dense layers to do progressive unpooling. So given our example of 256, 128, 64, you'd have 64, 128, 256. Finally, when we're done with all that, we want to make a final layer, okay? And that final layer is we're going to want to reshape our output, because this is the identity function. And some of you just noticed this isn't indented. It should be. Okay, so first, the number of units is going to be equal to whatever the input shape was to the model. Okay, that's how many units we want, or nodes. Okay, each one of those, okay, so those are our pixel values. We want to map them. These are real values between 0 and 1. Remember, our input was normalized between 0 and 1. So the activation function that's going to squash all the outputs between 0 and 1 is a sigmoid. And that's why we use a sigmoid. And then finally, we're going to reshape that output back into that image shape. So that's our image reconstruction. So here's an example of me training one. Okay, this was for minced. So you can see my layers were 256, 128, 64. So I create an input object. I then create the encoder, given the inputs and the layers. I get my encoder output. And then I create the decoder, giving the output here as the input here, the layers, of course, and then the input shape. Okay, then I just put the model together. That's my autoencoder. I'm going to compile it because I'm using sigmoids. That's going to be a binary cross entropy. And then when I train it, really the only thing here that's important is I use the images xtrain for both the training data and the label. Okay, so let's now move on to convolutional autoencoders. So autoencoders that use nodes or hidden units are actually computationally expensive for larger images. They're just not practical. So for larger images, we use deep convolutional autoencoders, and they're much, much more efficient. So instead of learning to pool and unpool nodes, they learn to pool and unpool feature maps using convolutions in the encoder and deconvolutions, also known as transpose convolutions in Decoder. Now, at this point, many of you might just not know what's a deconvolution or a transpose convolution. So I'm going to give you a quick explanation about the differences. So by now, you would be familiar with the idea of feature pooling in a convolution. That is, when we set the stride to 2, whatever we output in feature maps is going to be 1/2 the height and 1/2 the width. In effect, we're learning to downsample. A deconvolution does the exact opposite. So if you start with these as the feature maps and you set the stride of 2, it's going to output feature maps that are 2 times as high, 2 times as wide. So what it's doing is learning the best way to upsample. That's the only difference between a convolution and a deconvolution. Okay, so let's look at the architecture for a deep convolutional autoencoder. So you're going to have your initial stem here that's going to do a coarse level feature extraction. Okay, then the learner part is going to effectively have your encoder, your decoder, your latent space. Okay, and this is where you're doing your representational learning into the latent space. And then the decoder is where you do your transformational learning. And then finally, you have a classifier, which is the learn task that you're going to do. So even the stem is part of the learned pooling, and the classifier is part of the learned unpooling. So let's go ahead and write one of these. Okay. So here we're going to do something similar in layers, except for layers, instead of the number of nodes, it's the number of filters. And again, it's going to be a list where it's going to be progressively get smaller. So we just spin through the list. And each time we create a convolutional layer of that many filters. And of course, it's strided. So we have feature pooling. So it's getting less, 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 less. Okay. And then finally, the output of that would be our latent space. So let's look at the decoder. Again, it's going to do the exact opposite. Okay, so you're going to give it that layers list. You're going to go through it in the reverse direction, reconstructing from the lowest value to the highest value. Okay, but now we're going to do a deconvolution. In this case, it's called conv 2D transpose in Keras. And of course, it's a strided deconvolution. So the feature maps coming out are going to be double in size. Then the last step is we need to reshape reshape that output to match the input. So here, the input being, let's say, was RGB, we're going to have 3 channels, and we're going to do our final deconvolution to learn to shape it to the output. And then we're going to return that. So that's our image reconstruction. Now, what size of latent space do we use? Well, you might think, well, the bigger it is, the more likely I can learn the identity function, and the better compression and more reliable my compression and decompression would be. Maybe not, because if it's too big, it may overfit to the representational space of the training data. That is, if it's too big, it may have over capacity and then overfit to not the training data itself, but the training's data's representational space. On the other hand, if it's too small, it may underfit, and we won't be able to do on the other side the transformation and reconstruction for the designated task, like the identity function. So what we want to find is the sweet spot between the two. So one way we do this, and we refer to it as a sparse autoencoder, is we're going to add a sparsity constraint to not overfit. And the concept of a sparsity constraint is to limit the activation of neurons on the bottleneck layer that outputs the latent space. So think of, again, the convolutional autoencoder. You get to that last convolutional layer, and it's going to output its output. We're going to flatten. That's our latent space. But the activation function here, in addition to being a ReLU, we want to do some further squashing of those values as it acts as a regularizer at the latent space. So in Keras, that's referred to as the activity regularizer. The word activity here really is referring to the activation, or applying a regularizer to the activation. And we're going to do it as the last layer in the encoder. And the value is going to specify the threshold, plus or minus around 0, that we're going to change back to 0. So it's what it's saying is these tiny, tiny little values that just don't contribute much, we're just going to treat all of them as zeros, and that's like saying no signal. And that adds a little bit of noise or regularization to our model. And a typical value used is like 1 to the power, 1 to the e minus 4. So let's go ahead and write an encoder that does a sparsity constraint. Okay, well, this time we want to set aside the last layer. So I'm just going to set it aside. Then all the remaining layers, of course, I do my normal convolutions. And then when I get to the last one that's going to output that latent space, I'm going to add the activity regularizer. Okay, so up to now, we've only talked about the identity function. You may ask, what else can we do with an autoencoder? Well, the next thing people tend to learn to do is what we call a denoising autoencoder. And the idea is that it's an autoencoder that learns to be an image denoiser. So we can say it like this: given a noisy image to output a denoised version of the image. A simple way of thinking of it is thinking of that you have some noise here, E, and what you're learning is you have a function that takes an image plus its noise and it outputs that image. So that's the function we're going to learn in a denoising autoencoder. So it's really easy to do one. Um, it, you don't have to change the autoencoder to do this. You can use your existing autoencoder. What you do instead is you change your training data. Okay, so in this example, I'm just going to get a random distribution of some tiny values. That's going to be my noise. And then what I'm going to do is I'm going to apply that noise to my training set to get a noisy version of the training set. Remember, these are NumPy arrays, so this operation gets broadcasted across this entire training data. And now when I train, the noisy training data now becomes my input. That's that X plus E. And my output is the original training data. And that's training an image denoiser. So we'll wrap up here with pretext tasks. So autoencoders can be trained without labels to learn feature extraction of essential features. Okay, and we can repurpose this ability beyond things like compression and denoising. And one of the ways we do it is we actually use pretext tasks to help initially do some pre-training of a model that we're going to train in a supervised fashion. And our purpose is we want to learn the essential features of the data. And we're going to use an autoencoder to do that. And by doing so, the model, not only do we want it to generalize to unseen data in the same distribution, but if we're really just learning the essential features, then in principle, it should be able to correctly predict when there's a small shift in the input distribution that we call data drift after it's employed. So I know this is a really busy slide here. So it starts like this. So we're going to take an existing model that we're going to do training. Okay, we've initialized the weights of it. We'll do warm-up training. If you're not familiar with that, we'll be discussing that in a subsequent session. But the purpose of the warm-up training is to get numerical stabilization of those initial weights. And we do it in a supervised fashion. Now we're going to construct an autoencoder. And what we're going to do is we're, in a sense, on that other model, we're going to tear off the stem. Okay, meaning we're going to just take the stem layers and the weights on the stem layers at the time we completed our numerical stabilization. And then we're going to make an inverted version of that stem. We're just going to reverse the layers the other way. And then we're going to tie them together where we have a latent space. So this stem convolutional group, like any stem, does that first course level feature extraction, but it also does pooling. And we're going to take advantage of that. So we're going to then do unsupervised training here, typically with the identity function, so that this stem learns the optimal way of extracting the course level features where there are just simply the essential features. After we're done with this and we're happy, we then take this now further trained stem and we attach it back to our original model, and then we do the final supervised training. And that's really it for pretext training. I have a little bit of code here just to show you what it would look like to wrap it up. So let's say this is the stem from our model. Okay, it's going to have 64 filters. It does feature pooling already. Then there's max pooling, which does a yet further pooling. Since this is the only convolutional layer, we're going to add the regularizer for the latent space to this one. The inverted one is just the opposite. If you're not familiar with upsampling 2D, it's just a reverse of max pooling 2D. So this with a stride of 2 would make it 1/2 by 1/2. This would make it two times by 2 times. Then, of course, we're going to invert our convolution here with our transpose convolution. It's going to be strided. That's our unpooling. Okay, they have the same filter size here, 5 by 5, but this time the number of output channels is 3, so that we can reconstruct the image. And here we are, we create the input object. Hypothetically, we're going to say its shape is 128 by 128.3. We create the encoder, right? And then we take the output from the stem and we use it as the input to the inverted stem. And that's our decoder. And then we just pull it all together, and that's our model. And that's all you need to do. Again, thank you for joining our session here.